All right, guys, this is the next part of the waves. This is going to be a special situation where you have standing waves, and this is going to happen if you can have an input that matches the frequency, kind of like pushing a little kid on a swing. And if you can match the way that the wave is going when it bounces back and match it up, you can have it building bigger and bigger amplitude. And so the waves that are moving in opposite directions will match up and they'll interact with each other constructively. So these are going to occur if you have the end of your string that are fixed. You're going to have a node at the end and an antinode in the middle. I'll do this in class for you, but if you think about it, if you send a pulse down and it hits a fixed end, how do pulses rebound off of fixed ends? Well, they rebound along the bottom. And so then if you match that one when it comes back and put another one in just at the same time, you're going to have a building amplitude. The same thing, if you get it so just the whole wavelength fits across here, it's going to get to a fixed end, it's going to bounce back, and again, you just need to match the same frequency of the wave bouncing back and you'll build the amplitude. In this case, I have one and a half wavelengths from there to there, and then again, it's a fixed end, so it bounces back opposite. And so I can match this up. This is our fundamental frequency. This is going to be our first harmonic. This is our second harmonic. This is our third harmonic. It turns out that, and again, I'll do this for you, that once you find out what that first harmonic is, the fundamental frequency, if we're saying that this is F1, in order to do the second one, you have to do double that initial one. To get the third one, you're going to triple it. So that fundamental frequency will be called. And again, I'll do this for you guys in class. And you'll see when it doesn't work out. Here's another picture of it. Our fundamental frequency, or our first harmonic, our second harmonic. It also can be called an overtone. So second harmonic is the first overtone. The third harmonic is the second overtone. And for a string that is fixed at both ends, so this would be like a guitar. It's just going to be the frequency, double the frequency, triple the frequency. So the lowest frequency of a standing wave is going to be the fundamental frequency. All right, so resonance is going to be what happens if you match this natural frequency and you're going to have a building amplitude. This is going to be from standing waves. It's going to be constructive interference. I'd rather you guys not think of it in this term. I'll show you how to think about what the harmonics are with this problem. So what are the first three harmonics of a note produced on a 45 centimeter long guitar string if the waves on the string have a speed of 307 meters per second? So again, you can adjust how fast the speed is by changing. You can increase the tension. Remember, our velocity is related to the square root of the tension divided by the linear mass density. All right, so our first harmonic, I always draw it out. And I'm saying that this distance is 0.45 meters. This here represents a half of a wavelength, this distance from here to here. If it was to continue on, that would be a whole wavelength. So that tells me so that for the first harmonic, my wavelength is 0.9 meters. So my frequency is going to be my velocity divided by that wavelength. So this is going to be 307 divided by 0.9. Which is 341. All right, two ways to think about this. This is the fundamental frequency. To get my second harmonic or first overtone, I just double it. To get my third one, I just tripled the original. I'm a little bit off the screen, so I'll move this over so you can see it. Second way to think about it, this length is constant. So now for my second harmonic, it fits a whole wavelength in there. So now my wavelength is the 0.45 meters. My second harmonic is going to be equal to this velocity divided by that wavelength. So we're saying that our velocity is 307, and we're saying that our wavelength is 0.45. And so when you put this in your calculator, you should again get 682. The third one, I'm going to draw the same. And now there's going to be 1.5 wavelengths. So if this entire thing is 0.45 meters, this distance is 2/3 of that, or 0.3 meters. And so F3 is going to be equal to the velocity divided by this wavelength. And the velocity is going to be 307 divided by 0.3, and again, we should get 1023. So the equation I find confuses me more. I like to visualize what it's looking like when it gets to the end and bounces back to have constructive interference. All right, so an example off of the AP test. To demonstrate standing waves, on one end of a string is attached to a tuning fork that has a frequency of 120 hertz. The other end of the string passes over a pulley. It's connected to a mass M as shown in the figure above. The value of M is such the standing wave pattern has 4 loops. The length of the string from the tuning fork to the point where the string touches the top of the pulley is 1.2 meters. The linear density of the string is 1 × 10⁻⁴ kilograms per meter. It remains constant throughout the experiment. And this is, for the most part, going to be constant. I know, like, if you add tension, the string is going to get a little bit longer. If you reduce it, it's going to get a little bit shorter. But compared to the total length of the string, that's not going to be a big part of it. Determine the wavelength. So if this whole thing is 1.2, that is a wavelength. A wavelength would be a half of that. It is 0.6. Determine the speed of a transverse wave along the string. Speed is equal to the wavelength times the frequency. So this is going to be 0.6 meters times my tuning fork, which it says is 120 hertz. So it's 72 meters per second. The speed of the waves along the string increases with increasing tension in the string. Indicate whether the value of M should be increased or decreased in order to double the number of loops in the standing wave pattern. I am going to want to decrease it. So my velocity is equal to my frequency times my wavelength. That's constant. That's the tuning fork, right? The wavelength is dictated by increments of the length of string. So my mass is related to the tension over the linear mass density, and that linear mass density has nothing to do with the m that's hanging off of it. So it turns out that T is going to be equal to big mg. So if this is constant, by lowering m, I can lower T, and by lowering T, I can lower V, and that's going to make my wavelength lower too. So I would say that lowering M lowers tension, T equals mg. The square root of tension is directly proportional to the velocity. Velocity is equal to the frequency times the wavelength. The frequency is set. So lowering V will lower lambda, because these are directly proportional. If a point on a string is that an antinode moves a total vertical distance of 4 centimeters during one complete cycle, what is the amplitude of the standing wave? In one cycle, it's going to go up, down, down, up. So if it's 4 centimeters altogether, that would mean this arrow is 1 centimeter, this arrow is 1 centimeter, that arrow is 1 centimeter, that arrow is 1 centimeter. So that would mean that the amplitude is only 1 centimeter. So our distance that that point travels is always 4 times the amplitude. I'm going to do this in class for you guys.